back. The last session for today. The next talk will also be on coded computing. It will be given by Draper from the University of Toronto. Everybody knows Stark. He's the president of the Information Theory Society. So if you have creative ideas, Stark is all yours.
Please, thank you, Krishna. And thank you guys, and Henry too. I will thank you guys for the invitation and for organizing all this and the semester. And thanks to everyone else for staying here through Thursday afternoon. So I'm going to talk about some work I've done with my student. Really, it's the work of my student, Shahrazad Kiani. So she's a PhD student, and it actually dovetails quite nicely with the talk just before from Aditya. We're going to use some of his stuff. A couple of people here saw an earlier version of this in Munich, so you'll see it again. And there's a question in it, hopefully kind of an open thing we haven't sorted out that hopefully someone might get interested in. Shahrazad's kind of moved on to other things for the end of her last project for her PhD. So the idea here is going to be coded computing, and like Aditya said, we want to deal with computational fabrics that aren't ideal. Maybe all workers don't return what they're supposed to do, or they only return partial amounts, that sort of thing. But we're also interested in, well, in a lot of tasks we have today, we don't need to compute exactly. And so we were kind of interested in what you might do with inexact kind of rate distortion analogs. And there was a particular paper that I'll talk that kind of inspired us, and we wanted to extend, which is what I'm going to talk about today. All right, the delay. Okay, so the motivation, again, is, we have all these very intensive data problems, big data sets, large training sets, things we want to parallelize the exploitation of. And when we parallelize things into the cloud, say, that fabric might not respond reliably or consistently. And so we're kind of motivated to see what we can do to leverage ideas of error correction coding, which is for reliable communications, into the domain of computation. We already heard a little bit about some of the motivating paper in the recent era. So again, we're going to have this notion of stragglers. So you have some of the rabbits there, and some of the slow turtles. And if you have some synchronized thing you want to run, the slow guys can bottleneck the outputs. And as like Amina mentioned before, in the question and answer, we have lots of causes that can come contention for jobs, maintenance, hardware failures we've heard about in other contexts, and there could be communication delays. So again, like I said, and we heard, we're kind of arbitrage these ideas from coding theory to build redundant and not identical computations. And the greatest success, as we've seen, has really been when there's this beautiful dovetailing of the linear structure of coding theory with the linear structure of lots of linear algebraic operations, which are often important, and hence that makes it interesting. So our earlier work actually kind of also aligns with the work that Aditya talked about. I'm not going to talk about this, but this was kind of our lead in Shahrazad's first papers, were on what we call hierarchical, deals with this notion of partial stragglers that, you're paying for compute, and well, if you get through half of the work, you don't want to throw it out. You want to kind of collect that information, even if it's not as much, and so you can do the sub-packetization sort of stuff. This kind of aligns at the same time with the stuff that Aditya worked on. After we worked on that, Shahrazad and I were kind of interested in the general idea that, well, maybe not only do you have things that the compute isn't behaving perfectly, but your results don't need to behave perfectly either. Maybe you can get away with inexact computation. So we're going to talk about that today, where you could trade off sort of time for quality. Time here is going to be a notion of time, kind of like we heard in the last talk also. How many people you hear from, which isn't exactly the same as wall clock time, kind of taking these ideas from this kind of epoch sort of sense into the true wall clock is difficult. Okay, so I'll go through this quickly because we heard about this, but the basic idea, I'll use matrix computation, is you have, you can take some matrix A and B, and you can partition A into two parts, and then generally when you think about a distributed compute system, you have this idea you have to partition the data, you have to distribute the data, that's in red. Sorry about the red-green, anyone's colorblind. The red has to go out, you have to compute, and then the green comes back in, and then you stack them back up. Of course, if one of the workers is slow, straggles, then you don't get something back, or you wait a long time, and that's the problem. So in that paper from Lee et al., the transaction information theory, 2018, kind of kickstarted the modern era, I guess, of this type of faulty computing ideas using coding theory. The simple example is this, single parity check on the matrices, where the third worker, you introduce a third worker, and you sort of mix the data first. So you have this data combination that you send out to worker 3, and then, as we heard, if you get, say, like worker 3 and worker 2, it's not just concatenation anymore. You have to, of course, cancel off this contribution here and then concatenate them together. So it's a little more complicated, but the idea is there. And also, like we heard about, there's different ways you can break down matrix products, right? So one is what I think Aditya focused on, mostly polynomial codes, where they're kind of this inner product. A1, B1 is the upper left corner, A1, B2 upper right, and so on. You can break up those in outer product. Those are mat dot codes. I'm going to build on mat dot codes today. So you get these outer product of matrices. And there are mixes of that too, right? Which for various reasons you might want to think about. So there's by now a whole slew of variations of these combinations. So we're gonna work off mat dot codes as our work today.
Is there any particular reason like this one have much nicer properties, or is it kind of you choose your one and do similar things?
I think as kind of came up in the discussion, they have different, how much computation is it? How much is the data how much does it cost to distribute data? So there are kind of lots of system level issues, I think, that come in. You can kind of imagine, even if the data is the same, this little chunk you have to feed back is smaller than this is the size of the matrix. So they all have these kind of variations. They have their, I walked my distance today, apparently. They have, pros and cons in lots of kind of system level issues, I'd say. Right, okay, so, and then we'll start going to sort of newer stuff, but the general thing that the dominant, I guess, kind of idea, coding theoric ideas are based upon polynomial, kind of Reed-Solomon-like things, where we turn the recovery problem into a polynomial interpretation. And so just to set up the work we're gonna kind of build off, here in mat.codes, codes, they use these two encoding polynomials. So you have your A1 plus X, A2, and then we have B1 of X plus B2. So you kind of pick the ordering of the data and in this case, the terms in your monomial basis to get a particular combination. So if you kind of go down and work through the product of these guys, down here you see that the term you want, A1 B1 plus A2 B2, that's what you really want, shows up as a coefficient in the center guy. Okay? So the idea then is if you distribute to a bunch of workers samples, often you set X equal to the index of a worker. So A of 1 times B of 1, A of 2 times B of 2, et cetera. If you get enough samples, in this case 3, then you can recover the polynomial and you can extract that center coefficient. Okay, so, now this was our kind of, the paper that came out from Jeong et al. That we thought was interesting. They're called epsilon-approximate mat.codes. So let me tell you what they did, and then that was kind of what we thought was pretty cool, and we wanted to sort of think about how to extend it in a couple ways. Okay, so this is the same encoding polynomial as mat.codes, and if you multiply this all out, here's that term. In this case, it's 3. My last slide, there were 2, so you have this middle term that you're still interested in, and then you have these lower order terms, and then the higher order terms, and there's this remainder term. Okay? So the idea in this paper is that, well, when I evaluate the A of X and B, when I pick the X's for each worker, if I pick X small, okay, this can imagine it's going to have some numerical problems, but if you pick it small, then this term gets even smaller because it's at a higher order. And so what you kind of end up with is the thing you're interested in, which is here, and I can kind of think about this term, or I guess the way I think about it is a little bit like interference. It's an interference from higher order information. But if you evaluate at these small x's, then the sort of remainder term is scaled down. It might not be that bad. And then the idea is that, well, you have some polynomial you're interested in, which is degree 2, plus some other interference stuff. And so I can get away with 3 evaluations to recover this polynomial, but with some interference. So it's an inexact recovery. Okay? So that's the idea in this paper. So that you can recover this polynomial, but it's not exactly going to be what you really want. And they call this nearly twice as fast. It's how they determine the paper, because you go from generally you need 2k minus 1. So these are degree k polynomials. K is 2 here. So you have 2k minus 1. So that's 3. Sorry, 4. 2k, 2. 5 here, I guess. N to k equals 3. So you get a lower degree. You're able to. K is not the degree. K is the more things you have to get. So you get away with only needing 3 samples to get back. So that's the k equals 3 rather than the 5 samples you needed originally, because the original was degree 4. That's what I call it, nearly twice as fast. And then the idea is, so you get that once, okay? And then if more people report in, a 4th worker, a 5th worker, et cetera, eventually you can then figure out what this remainder term is and get exact recovery. So it's kind of a 2-step thing. You get an approximate thing first, and then a little while later you get an exact thing. This is not our work. This was our motivating work. Yeah.
But what about the lower terms?
So again, you're going these terms here. You mean? Yeah. Well, I'll come back. This down here. Oh, so okay. So I'm saying what you try to recover is this polynomial, this p of x, which is the first. This is the thing you really want without the higher order terms, but you don't get it back exactly because of this interference. And then, but if you get this approximately, now you have an approximate version of p of x, and you pick out the coefficient that's which is now not exactly the blue thing because it's inexact, which is associated with x squared. Does that explain what I was trying to say? Okay, so let me kind of visualize this a little bit just graphically, because I'm going to use this to develop kind of our idea. So this is you can think about A1, A2, and A3 as like the yellow, red, and blue box. And I guess it's, well, it's depending on what order. It's B1, B2, and B3 are going to be the red, green, and gray box. And so general matrix multiplication is you have these outer products. You take these 2 things together, so they give you this kind of box, which is your matrix, which is this mixture. That's what I'm trying to show here of these two colors, those 2 ones, and so on, right? And then if you kind of picture this with what's going on in mat codes, one thing is the order of this one is reversed. If you go back, you'd see that. So the B3, I guess, shows up with the 0th order term. But anyway, so you multiply this out, and what I get out is here's that coefficient, and I get out the sum of these coefficients. That's the idea of mat codes. Okay. So then the idea in these epsilon AMD codes is that these are those high order terms are like noise, type of interference. And what we were interested in is how do we generalize this? Because you remember what happens is you recover this approximately once kind of 3 workers report in, and then once enough workers report in, then you recover the whole thing. So can we get this to kind of more than 1 step effectively? We're interested in that. And to do that, we were interested in, well, this coefficient here, which is the sum of 3 terms, we kind of want to move it around somehow. We want to break it up so that the information is not recovered all in one place, but it's kind of hidden in multiple coefficients. So I'll show you how you can do that. So this is the AMD, epsilon AMD, this is the previous work. And so here's a different way to arrange that second polynomial. So you can just see the first polynomial stays the same. The colors have switched a little bit in the second polynomial. And if you kind of multiply this out, you see this term, which has degree 1, is this combination of the green and the red, and whatever this is, brown and yellow. And those are 2 of the coefficients that were summed up there. Okay? So one of them has moved earlier in terms of like lower degree, which would mean in this kind of approximate recovery thing, you can find it sooner, but you don't get the whole coefficient. And then the last coefficient, the last piece of that coefficient you're looking for has shifted later. So then I get this kind of I get something a little earlier, which was good. Still, this is still the same degree. So by the time I get this one, I have exact recovery. Sure. Okay. So this is, are we good? This is the same in epsilon AMD, which is the earlier work. This is the same set of polynomials that are in MatDot. Okay, and so all we've done here is this second polynomial. We've kind of rearranged the terms. So I think this was B3, B2, B1. So it's like the B matrix is B3, B2, B1, or whichever way you split it up. And you see we have a different order here. So this one has gone here. Those two have gone there. Okay, so just you can write these all out with letters. I was just hoping by images it would show. So these are the three. These things get added together. These mixtures for the third term. That's what you're interested in. That's the coefficient. And color coding. A little hard to see sometimes, right? These two have shown up over there, and this one has shifted back. So some has shifted forward, some has shifted back. Okay, there's probably some principle here that I don't understand yet about what you can do to shift these things around, but it's one of the open questions. Okay, so. All right, great. So we can get a lower fidelity. So then again, the idea is that if you get two evaluations, you can kind of get this back in exactly. And then if you get a third evaluation, well, I can sort of recover these coefficients, not exactly, but I can recover more of them. And the way I kind of think about it is like, and you'll see this in the results, when I get the next coefficient, it's like, there's like kind of a, or maybe I'll explain, I'll hold this to the next one. The next one's a little easier, okay, to give you the way I think about this thing. Okay, so here's another, here's the one from before. Okay, I'm just saving. This is the example I just gave you, bottom half of the previous slide. So let me give you a different set of polynomials, slightly larger. Okay, so here what I've done is I've put an extra power on that blue box. I put a 0 coefficient there. Similar over here, and now I've spread out these three terms of interest, sort of the three coefficients of interest. So I have a bigger degree polynomial. One of the terms has shifted even forward, so I get kind of my approximation of that, whatever that contribution to the AB product that I want. I get it after my first worker reports in, and then my second reporter works in. I can kind of approximate this polynomial. I can still select out that. Then as another worker reports in, I can get an approximation of this. This is still all interference, the higher order terms. Okay. And so the way I kind of think about it is it's kind of like a signal to interference and noise ratio. As you get the higher orders that you can kind of estimate this one or estimate this one, it's kind of like your signal power goes up because you have more information. You have some ability to estimate, or the contribution from this guy, and then this guy, and then this guy. So you're going to get these kind of, and you'll see this in the results, you get these kind of steps where when I pass this one, I get kind of an improvement because I have information about 1/3 of the three coefficients I want, then 2 of the 3, and then 3 of the 3. So I get kind of a discrete jump improvement. In between those steps, I get a smaller improvement because I'm able to sort of estimate this interference term and cancel it off. So you'll kind of see those two effects when I give you the results. And so, if you kind of just think about this as convolution effectively, right? I've just spaced out the polynomials a little bit, so I avoid interference, right? So I make sure that in both this example and this example, all the coefficients that I want, which are the sum of these three coefficients, either show up by themselves or some of them, right? That may not be the best way to do it. So that's how we've done it here. Avoid interference. We call this 3 group because there's 1, 2, 3 groups. That's where all right. So just to again say, kind of highlight, and this is so I think we think about this as kind of there's some amount of interference and there's some signal, and you accumulate signal information as you go past these circled chunks, and you reduce interference as you go in between. You'll see that in a second. The total error is both about sort of some approximation error, which is because you're missing those pieces. Say early on, you don't have this piece here. And there's also precision problems. So in the examples I'll show you, we use some of the work like Aditya talked about, where we use complex numbers. The earlier work, they just used real numbers. This does have the challenge of more computational power, but it helps out, as we saw numerically. The other thing we do is we randomly permute the order of these guys, because you don't really know in reality which of your matrix products is going to have the higher norm or the lower norm. So we just do a kind of a uniform shuffling to avoid those sorts of effects. Okay, so here are some examples. So in this case, there are 40 workers. We're multiplying two matrices, 100 by 8,000. We're splitting into a bunch of subblocks. So those are the subblocks like A1, A2, A3 up to AK. So there are 8 things you want to recover. So that means for the standard mat.code, it's 2k minus 1, which would be 15. That's the standard recovery threshold. In this case, we generated them at random, normal entries. And here's the epsilon AMD, so 15, and this is where the idea is it doesn't do anything, and then it gets partway down, halfway along, and that does full recovery once you get to 15, 5 minutes. Okay. Here are 2 examples of our designs. So here's with the first group, you have to get 6 workers to report in to get that first step, or 8 workers. This is the 6th worker, you get your first step. Here's the 8 workers, you get your first step. This is where you sort of see, this is the improvement from getting the first coefficient. There are only 2 coefficients here. And then this is, as I kind of can figure out the polynomial a little bit better, this is from sort of reducing the interference from the higher order terms. And you get the most gain the first time, a smaller gain after that. It doesn't really help that much because it's like x to the power. 0.15 gets exponentiated, and so you don't see much more gain. Okay, so I have 5 minutes, so I'll tell you. So we looked at this, and then we also thought about one other thing. So also, as Aditya talked about, polynomial mat.codes use this monomial basis. So they have this challenge when you want to invert the van der Waals matrix. So other people have looked at using like orthogonalized polynomials. And so we looked into this too. So these were also mentioned, orthomat.codes by Vivek's group, also Lagrange polynomials. So we have another approach that works with these types of schemes separate from the mat scheme. And because I just have a couple minutes, maybe I'll just kind of go through it quickly. These work a little differently because effectively what you do is you have these evaluations. Again, you have evaluation polynomials like before. You evaluate them at certain places, and then you decode, so you get A, B back. But then it's not a coefficient anymore that you're looking for. These things are orthogonal. The T's are orthogonal. So basically, you want this inner product, and these things cancel out. So you could integrate to take the inner product with, there's a weighting function in there. But if you take particular choices of the y's, for example, then you can actually get this inner product equal to just this summation, which is a lot easier to do. So you evaluate at certain points and sum them up rather than actually trying to integrate that polynomial over the -1 to +1 interval. Okay, so I'll just show you how we integrate it and then compare. So our idea here, which I have to say I don't like as much as the first idea, was to pick these evaluation points to be close, a little kind of variability around one point, so that we get kind of diversity of our evaluations. Let me just show you how we did this. So we took a code, okay, we have a length n code, and we split it into groups, okay, and each group has like a point that they want to evaluate at, and then we took little variations around that point. And so the idea of, and then what we did when you report in, you kind of, you take your evaluations, there's certain slight perturbations around around your sampling point, and you average them. That gets rid of a little noise, and then and these together form your approximations of the polynomial you want. I know I can tell people more about it afterwards, given the time. It's a little bit like kind of a slight variation, but it's a little bit of repetition coding going on within these groups here. And just to show you how it works, and this is, if you were to take the standard like orthomat.codes here, and you don't have the permutation, so epsilon equals 0, then what happens is you have to kind of wait, because you might be unlucky and some group won't work in, so it takes a long time to get there. But these little permutations lose you a little bit early on, but then you can get, you can do inversion or decoding and get exact recovery at that 2k minus 1 point. This is a different approach, which is just splitting up using two mat.codes we thought was a baseline, recover in 2 pieces. Okay, so that's, oh yeah, oh, and this is comparing them. So you can sort of see the combination, the comparison between the, these are the group ones which have those discrete steps, and then these are these second, the point-based. Okay, so to wrap up then, so this is our group and what we call it layered successive approximation coding. You have this multi-layers and epsilon AMD, and you can get this trade-off between approximation threshold and relative error. There's lots of interesting things. How can you get, are there better polynomials that don't just kind of avoid the interference? That's the kind of question Shahrazad wanted to work on something else for her later PhD project, so curious. That's a question I have kind of sitting around. There's also a question, the partial recovery stuff. This our version, we called it hierarchical, but partial stragglers, how can you combine these with that sort of notion? And as Amina mentioned too, there's also a question of how do you partition the data into the size of the computations? Because what we really care about here is like wall clock time. We don't really care about how many workers have reported in. That's not actually the metric of interest, but it's not easy to go, these plots are easy to make, and the other plots you need some good statistical model, or you actually have to run it on EC2 or something, or you have to, and some parts of EC2 are not very straggler endemic, right? So it's takes some work to go from these to that sort of metric of wall clock time, which I think is what we really all would do. And just to announce, since it was Super Tuesday, if you have any students who want to come up to Canada. Okay. Okay, so how did I stop there? Thank you.
In your approach, so I understand, so you're trying to spread things around. So first, your overall degree of the polynomial is higher, and some of the useful terms are actually lying on values where the the degree of the corresponding monomial is higher. Like here on the bottom one, it's lying at x to the 6.
Yeah.
So how does that affect when you try to decode? Because you are using small x, and that term will be buried somewhere, right?
Yeah, so that's definitely one of the numerical challenges here, right? Because you have to go for longer to do it. That's definitely an issue with this approach.
So is it true that that particular block is recovered with less fidelity than the others or something?
Oh, I see. Probably, we could look, if you'd like afterwards, we can look, and we have those numerical plots in the paper. I can't recall, but it would make some sense. I don't quite remember them showing up that way, but I wouldn't be surprised, but I'd be happy to kind of look through it with you. But I mean, this is the challenge of it. You'd want this to be a more compact polynomial, right? So that's why I don't know if this is the best way to do it.
So we are on the same slide. So I'm just curious that by this expansion, the amount of work that is being done by each worker is rather higher.
No, it's the same amount of, because the workers still have because the amount of work done by each worker is basically set by how do you partition. So the partitioning here is still my A matrix goes into 3. Right? It's just that you have to wait for more workers to get back to you before you can get that. So if you had like 5 workers, then you definitely wouldn't want to use the scheme, or you would never get the 6th one back, for example.
Yeah. And then just another follow-up, which is similar to the previous question that I was asking Aditya. I think again in this setting, the dependency aspect might add an interesting angle to see, and that might actually help because you have these kind of subtasks that the workers are computing.
Yep.
Since they are dependent, it would be interesting to see how that impacts the approximation aspect. It might help in terms of getting to the approximation quicker.
So that would be, yes, and so we looked at a type of dependency, which is dependency within the matrices themselves. So if they're not, yeah.
The sub-task could be like linearly dependent. The sub-matrices distributed.
Yep.
Yeah. That is kind of one common kind of dependency that arises because of stars and other kind of matrix, high-level matrix multiplication.
Great. Okay. Thank you.
Just the fidelity of the matrix will really depend on how the blocks behave, right? Just asking. So let's say, for example, here the blue-gray block has high numbers,
Yep.
and you don't get to decode that, right? Then the error will be higher.
So say that again. So this will be higher. This is where like, yeah, the numerical stability might be more of an issue. Yes.
Yeah, so even if you don't get to decode, right, I'm not worried about the degree now. I'm worried, let's say only 4 workers report, and I get to only decode the first 2 blocks.
Yes.
But my matrix is the sum of 2, right? I only get the first 2, and then most of the numbers happen to be in the 3rd block for some reason, right? Then the fidelity will really depend on how those blocks behave.
So I think, okay, so I'm not, let me see if I followed. So certainly if like this is a high norm block or something,
Yeah.
that's gonna cause a problem, for sure. So one thing we did, but it only deals with it on averages, so we shuffled, you know, the blocks around ahead of time to deal with that. But that doesn't mean you might still be unlucky and have the worst stuff end up there. That's definitely an issue, yeah.
Okay, so all those error plots there, it's kind of like average case errors.
Yeah, okay, yeah, thank you. I mean, yes, these are average. So we average over, you know, a bunch of realizations.
Yeah, IID matrices, it doesn't matter. You don't have that problem.
Well, I mean, assuming it's balanced, yeah. Okay, so we also did ones that they weren't IID, and then
Sorry, one quick question on this stuff. So the average relative error, is it the Frobenius norms?
Yes,
Or decoding minus what you're expecting
yes.
normalized, or is it just that?
I think it's I think it's the Frobenius norm normalized.
Normalized by the actual.
Yeah. We can look at the paper. I can double check.
All right, let's thanks, Doctor.
And let me thank, I think Shahrazad may be watching, so thank you, Shahrazad, for your work. The students. Okay, thanks everyone.